Okay, so we will now describe some mechanisms that can be used for communication among processes that are running in different machines. Okay, so these are called sockets, remote procedure calls, and remote method invocation. So let's look briefly to each of these sockets. So sockets can be used actually to communicate processes over internet. Okay, so a socket is defined as an endpoint for communication, all right, and it can be identified, each endpoint can be identified by an IP address and a port number. For example, a socket in one end of the communication may be referred like this, with this IP address and having port number, for example, 1625. So it refers to port 1625 on machine with that IP address, on a host or on a machine, on a system with that IP address. Okay, if you run an application that opens a socket, okay, that socket may be identified in that application, in that system with that port number. Since each system, each machine with the same IP address like that can have lots of processes, and each process may open or use one or more sockets, and each socket has to be identified uniquely in that machine. We use port numbers for that purpose. Okay, each socket in that machine will have a different port number. So one of the port numbers can be something like that, 1625, that's assigned to one of the sockets that is created by an application, okay, to communicate through that socket to somebody else, to some other process running somewhere in the internet. Okay, so you can in this way create sockets, okay, and then use them for communication between two other processes. So communication consists between a pair of sockets. In one machine you can create one socket, and in one process, and another process in another machine can create another socket. Okay, so using these two sockets we can enable those two processes communicating. Okay, if we have in one machine, for example, 100 processes, each using one socket, that means we need 100 different sockets created, each having a different port number, although they have the same IP address. Okay, therefore to uniquely identify an endpoint, we have used the combination of the IP address and port number, and then you can use that socket. So basically the system provides you a set of functions, an API, socket API, that you can use to create sockets and use them to send information. Okay, there are send and receive system calls that can operate on sockets that you have created, and using those calls you can send and receive messages through the sockets. This is possible. Okay, so then as a result, what will happen? We may have a process here that has created a socket. Okay, assume we have a process web server that is running in that machine, okay, with that IP address. And so web server is just a process. Assume it has opened a socket with that port number. Okay, so there are actually some services like a web service, web server, like FTP server and so on. They have well-defined port numbers. Okay, a web server opens a socket and assigns the well-defined port number to that socket, so that other processes that are running remotely, when they want to communicate to that web server, okay, they just indicate the IP address of the web server or domain name. Okay, they don't have to use a different port number, because the port number is a well-known port number. Port number 80 is used, for example, always for web servers. Okay, so for some well-defined services like web server, FTP server, and so on, we have well-defined port numbers. But similar to that, you can write your own server and assign that to a totally different port number. Okay, so in this example, we have a web server that is running in that machine with that IP address and using 80 as the port number. That web server can open the socket and may wait for the connection requests there. Okay, so a web browser, for example, running on this machine in host X, for example, may open a socket with that port number 1625 and may use that socket to establish connection to here. Okay, as a result of that, we may have a connection from this socket to that socket. Okay, and that connection is actually done by the internet protocols. So this is the topic of the computer networking course. So internet protocols, the networking protocols can establish a connection and provide the means that can be used to send messages from here to there. Okay, internet protocols and internet architecture and internet infrastructure transports the message from here to there. As the application programmer, you don't have to deal with that. You just have to know how to create sockets and how to use them to send and receive messages from here to there, okay? So your web browser is implemented like that. Similarly, you can also write an application program, a program that creates sockets and use them to send messages and receive messages from a remote process, okay? Then what will happen after you establish the connection and you have now two sockets identifying the endpoints of the connection. Each connection has two endpoints, one endpoint and another endpoint, and each endpoint is identified with something like that. So two endpoints, one connection is therefore identified with these four parameters: the source IP address, source port number, destination IP address, destination port number, okay? If we have another browser that establishes the same connection to the same socket there, even though that part of the parameters is the same, here we will have a different machine with a different port number. We can have another process here that is in the same machine, but that process will use a different port number. Therefore, a connection between two processes can be uniquely identified, okay, in one of those machines. Therefore, you can easily get the message from the correct sender and send the message to the correct receiver and so on, okay? So this is socket communication, and there is a socket API that you can use to send and receive messages over the internet to some other processes that are running in remote machines, okay? This is possible. And another mechanism that we can use to communicate to some other remote machines and processes there is the remote procedure call. As the name implies, you are calling a procedure actually that is run remotely. You are calling a procedure that is part of a process that is not here on this machine where you call, but on some other machine. Normally, you know in your application how to call a procedure, right, or a function. It's very easy, right? You just call the function and then give some parameters in your program. For example, main itself is a function, and there you can call some other functions in the program as a statement. But it is also possible to call a function that is not part of your program, that is part of another process, another program that is either running in the same machine or in some other machine. But for that, you have to have a mechanism, RPC, provided by the system to you, so that when you do the call, that call will be intercepted by that mechanism, and actually messages will be sent to the other system, and the procedure will be run there, and so on. So the difference between the remote procedure call approach and the socket communication is this. Here, you explicitly build the messages. Send them, receive them, process them. You do that explicitly, and you work with messages, okay? Here, in remote procedure call, you are not working with messages. You are working with functions. You call functions. You get the return value or the results. This is how you perform your communication. You call a remote procedure as if you are calling a local procedure. Hence, for the application programmer, the task is a little bit easier because every program is calling functions, and you know very well how to call functions in your applications, right? Similar to that, you call a function that is not run here, but in a remote machine. So the job of the application programmer is a little bit easier in this approach, okay? So remote procedure call abstracts the procedure calls between processes on networked systems. In order to enable a process here to call a function remotely, the system should support RPC, remote procedure call. For that, it provides stubs where we have a client-side proxy, okay, provided by the system, for the actual procedure on the server. So when you call a remote procedure in your application, as if you are calling a local procedure, that remote procedure the call is intercepted, and client-side proxy is invoked so that it will process that call, that procedure call. What it will do, it will create a message. In that message, it will put the name of the procedure and its parameters, and then send a message to the remote machine where the procedure will be actually run, called, okay? So after you call that, actually the client-side proxy intercepts your call, prepares a message which includes the name of the procedure and parameters and so on, and send the message to the remote machine where there we can have also another step, receiving the message and getting the parameters, name of the function and so on, and executing the function there. And then returning you maybe the result code or return value. After that, the stop will get the return value, and now the function that you have called will return with that value, okay? So as the application programmer, you just call the function. But actually, while that function is executed, the client-side proxy is executing, sending a message, receiving the result, and so on, and then giving you the illusion that the function is actually executed locally. All right? As the application programmer, you are not noticing anything. But underneath, there is something happening. Messages are sent and received, and as a result, the return value is returned, and any parameters are returned, and so on. Okay? So while sending, so now the task of building a message is given to the client-side proxy. If you do not use RPC, remote procedure call, then that task will be the task of the application programmer, your task. You will build a message, put parameters there, and so on, send there, and there at that remote machine something will be executed and will be returned, and so on. Okay? So therefore, it becomes easier for the application programmer to call remote services. Okay? And one issue here is a term will be introduced, which is the marshalling of the parameters. As I said, when the client-side proxy intercepts the procedure that's called remotely, okay, at the local machine, then it builds a message and it puts the parameters. While putting the parameters and name of the function, it follows some standard. Okay, this is called marshalling the parameters. Because this has to be standard, because maybe the RPC, the other end of the RPC is implemented by somebody else. All right? The remote machine may be not in this country, but in a different country, implemented by somebody else. So there has to be some standards. There has to be a way of sending a message from here, and the other end will understand the message. Therefore, we have to use the same formats, the same encoding, and so on. And this is the marshalling of the parameters. Okay? So this is the RPC, and let's look to the third method, remote method invocation, that is possible in Java environment. Okay? So this is very similar to RPC, so, but it is a Java mechanism. Okay? So similar to the RPC, remote method invocation, RMI. What it allows is this. RMI allows a Java program on one machine to invoke a method on a remote object. You all have written Java programs, right? You can create an object, you can call its methods, and so on. So all these are happening as part of the same program, right? Locally. So similar to that, an object may be not sitting in your program, but it may be sitting remotely, and Java RMI allows you to call a method of that remotely, okay? Remote method invocation. So that in this way you can get a service done here, okay? So a service that is implemented here now becomes accessible to you here, okay? You can just call that service. So that service will have an interface, a function that is to be called to invoke that service. So you just call that method or function, but that service is not actually implemented here and running here. That service is running there, okay? And it is run here. So you just invoke it from here. Then the remote method is implemented and also run here. And the service is actually performed here, and the results are returned back to you, okay? So Java has such a feature as well. In this way, you can have that program and that program communicate, and this program, for example, this client, can ask that server to do service, some service for this client, okay? So a client service system can be implemented in this manner. Similarly, the Java RMI requires also marshalling the parameters and so on, so that the parameters of a method that is to be executed remotely, those parameters has to be put into a message, and that message has to be sent. The name of the method has to be included in the message, and so on, so that when that message is received by the remote and other machine, that machine will understand which method to execute, what are the parameters, and so on. After that, it will execute that method there with those parameters. It will obtain the result, and the result will be returned. For example, the return value of the function will be returned. It can be a Boolean return value, for example. Okay? So this is end of the lecture about processes. Do you have any questions? So what we have done in this processes lecture is this. We have seen how to create processes, how to terminate processes. We have seen the process concept, how the kernel maintains and manages processes, okay? What kind of information kernel maintains about the processes, the PCBs. The list of PCBs that kernel maintains is called process table sometimes, okay? So if there are, for example, 100 processes that are created in the system. That means we have 100 PCBs structures created in the kernel to keep track of those processes. Those 100 PCBs can be just put into a table, into an array, okay? So this is called process table. So we have seen all this, and then we have seen the cooperative processes. We may need to develop applications that are not creating just a single process, but many processes that are cooperating, all right? Meaning that they are sending information to each other and so on. We have seen some mechanisms that can be used, all right, to enable the applications or programs, processes to communicate with each other. IPC mechanisms, very important, okay? And then we have also seen some mechanisms that can be used to enable communication between processes that are running in different machines. A client process here and a server process there on a different machine, connected together with a network like internet, and they would like to communicate. And some mechanisms that we have discussed can be used for that, like the sockets, RMI, or RPC can be used to invoke services remotely and to communicate with a remote server, okay? I may be a process, a client process, and I may connect to a remote process server and get some service done there, okay? And the mechanism that I can use for that purpose may be sockets, or it may be RMI, or it can be, if I am using Java, or it can be RPC, okay, remote procedure calls. So this is the discussion about the processes. So we have to stop with this discussion, and we will start with a new topic, with a new chapter. Do you have any questions at the moment? Yes.
RPC ile RMI
So RMI is Java specific, okay? It is right. RMI, for example, in C you cannot have RMI used, okay? So, but you can write a C program that uses, for example, RPC, okay? Any other questions? Okay, so this is end of the lecture about processes. Basically, this is the end of chapter 3, okay? So now we will start with chapter 4, and which is about threads. So we will introduce now the threading concept and so on. So now this lecture will be about threads, and we will and here again we are talking about the chapter 4 of the OR textbook, but we are also getting some content from another reference book that we are using, Modern Operating Systems by Tannenbaum. And in this chapter, what we will do is, in this lecture, we will introduce you the threading concept, multi-threading, what is that, multi-threading models, and we will introduce you the threading libraries, what kind of functions can we use to create threads and use them. And we will talk about some threading issues, what are the issues that we have to be careful about. And we will talk about some examples from real operating systems. How, for example, Unix provides you with some set of functions that you can use to create threads in Unix, okay? And so on. And the objective of this lecture will be to introduce you the notion of the thread, the concept of a thread, and to discuss the APIs for the threads, okay? For creating and manipulating and using threads. There are several APIs available. Pthreads is one of them, Win32 API or Java API. And we will also discuss some issues about the multi-threaded programming. So what's a thread? And so this is we will start with our discussion with introducing you the threads. So what's a thread? So we will start with that discussion. Before that, let's look to remember what a process was, okay? So if you consider the lifetime of a process, it is executing, right? The instructions are executed one by one, okay? Sequentially. So a process has a single thread of control or execution sequence or execution flow. What does it mean? So a process starts with some instruction, okay? It starts executing with the main function, okay? Then it executes the instructions in the CPU, okay? So if you look over time which instruction is executed, you will see that the instructions are executed one by one, one after another. Sometimes we jump to a point and start executing there. We loop and so on, right? So now if you just draw a line, for example, if you just write the instructions that are executed, sometimes you re-execute the same instructions, you loop and so on. So you have an execution sequence of instructions, okay? Execution flow, all right? that looks like a thread, okay? Because you have sequence of instructions, sometimes looping several times, and then it's going, continuing, jumping somewhere else, okay? At the end, you have a diagram that is showing the instructions that are executed like a thread, okay? So this is called a thread of control, okay? So a set of instructions that are executed is the control, okay? So we have a thread of control. For a process, we have a single thread of control, meaning that we have a single execution flow, execution sequence, right? So if some instructions are executed as part of that process, and when we block on something, for example, we executed an instruction that requires some I/O operation, then what do? We block the process. No instruction, no other instructions of the process execute anymore. The I/O is done. During this time, the process is doing what? It is waiting, right? Blocking. So the execution sequence has been suspended at that point, right? And then when the I/O is completed, we continue from where? From where we have stopped, right? With the same instruction or the next instruction after that, we continue, right? So when such a process is blocked on something, during this time, that process, the system for that process, okay, the CPU is not doing for that process anything, all right? So you can not do any activity as part of that process in the CPU, right? For example, that process has initiated the I/O at that instruction, and then it is suspended. It stopped for a while, all right? So the I/O for that process is done, but the CPU cannot be utilized anymore by that process. So if a process blocks on something, no other activity task can be done as part of this process during this time, okay? You cannot run this process anymore. But sometimes you need this ability. What is that? You need the ability to concurrently run several tasks as part of the same process. For example, you may run your program which may do at some point keyboard I/O. So it is blocked, all right? It is waiting for the user to type something, which will happen maybe 10 minutes later. During this time, the process cannot be run. But that process may do something if it is permitted. May, for example, take backups, write the content of the memory to disk. For example, it can be a word processor, okay? So it is blocked to get input from the user, but it may actually auto-save the content to the disk during this time while waiting. But a single process, a single-threaded process cannot do that because it can only do one activity at a time. It can do I/O, or it can run in the CPU, okay? While doing I/O, it cannot do something in the CPU or with the network, okay? So, but this is not the best way of considering the process or designing processes. We may want actually a process to concurrently do several tasks. For example, while doing disk I/O, it would be nice to have the process also do some computation in the CPU and also maybe some networking, okay? Sometimes this is a good thing to have. So, but with a single-threaded process, we cannot do that. So far you have usually worked with single-threaded processes, and every such process has at least one thread, okay? So even though the threading is not supported in the system, you always write a program that is run, we say that it is actually a single-threaded process. We have at least one thread, okay? Even though you are not creating any threads, you have at least the main thread of control, right? Execution flow, we have one execution flow always, execution sequence, which we call thread. So every process has at least one thread. But now in this lecture, we will see how we can create more threads for each process. A process can have multiple threads of control. This is possible in a system that supports threading. In this case, what will happen? Threads will run in a pseudo-parallel manner, concurrently as part of the same process. So one thread will be responsible to do disk I/O. One thread will be responsible to do network I/O. One thread will be responsible maybe to do keyboard I/O, okay? So while one thread is waiting for the user to type something, another thread may go and save the content to the disk. Another thread may, for example, may do some computations in the CPU. Assume you are working with Excel, okay? In there, assume you have an Excel sheet that has 1,000 columns, 1,000 rows, and so on. Very big Excel sheet where you have formulas in the cells and so on, right? What you can do, from time to time, you put some new cells, some new values are entered into the Excel sheet. So that means you are inputting, right? For that, for example, a thread can run and get the input from you, from the keyboard. But another thread, while that thread is waiting for the user's input, another thread, for example, automatically can go and save the content to the disk. Another thread can refresh the formulas, recompute the formulas in the cells. Okay? So all these threads can work as part of the same application, as part of the same process, which is the Excel that you are running, for example, okay? A spreadsheet program. So it's a good thing to have threads so that we can have several activities going on as part of the same process instead of just a single activity. That means we can have several execution sequences, flows, threads, instead of just having a single thread in the application, okay? Of course, all these threads will share the same text data segment. The program code will be shared by all the threads, plus the data global variables will be shared, okay? Otherwise, if you are not sharing them, that means you are actually having different processes. So it will not be different than the processes. So let's look to the threading concept a little bit more. So far we have seen single-threaded processes where you write a program and then you start running the program. Then the program is loaded into memory. It needs that information to run. What is that? It has some instructions to execute, machine code, and it has some variables, storage allocated for the global variables and so on. So the memory layout of the process, it needs that to run. It is loaded into memory and it needs CPU, right? While it is running, it starts with some instruction and it runs, okay? So, for example, it can be the first instruction of the main function of the program. So it starts running, okay? So your program, this program may do some I/O. So it may block at some point to do some I/O, right? So then, during this time, when it blocks, it is no longer using the CPU, right? So then, after the I/O is completed, it can continue running in the CPU, okay? During this time, it is running in the CPU, assume. But when it blocks for a while, for example, for 10 minutes, it is not utilizing the CPU, right? So how much we block depends on what kind of I/O we are doing. Maybe 20 milliseconds, 50 milliseconds, or maybe 2 hours, okay? Then it may block again, and so on. It may continue, of course. So this is one thread of control, execution sequence. Of course, we should have some loops here, which I am not showing here with this simple diagram, but we have actually a thread of control, right? We are looping, and then continuing, and so on. We are jumping maybe to a different function, and so on, jumping, and so on. But we have a single execution flow like that, all right? And so this is what a single-threaded process is and how it is executing. In a multi-threaded process, what we will have? In a multi-threaded process, we will have, again, a memory layout, memory image for the process, a set of instructions, and global variables, and so on. We will create multiple threads now. They will operate on the same set of instructions, and they will use the same global variables. This is the idea. Otherwise, if you duplicate them, that means we are creating a different process. We don't want to create a different process. We would like to create different activities, several activities, as part of the same process. So all these different activities will execute actually or generated from the same code here, and they will operate on the same global data, okay? Global variables. But each thread will have its own stack. So let's see how a multi-thread process could execute. So then now what will happen? A multi-thread process may create several threads. One thread is running, the main thread initially, okay? Every process has the main thread, right? That is initially run. So that can, for example, as soon as the main thread runs here, it may create several threads. Okay, so we can have several threads created as part of the process. So when of those threads block, okay, the main thread, for example, you have now the opportunity to schedule another thread and run it in the CPU, okay? So now, this thread is not only schedulable entity. So in this case, this is only the schedulable entity, okay? When it blocks, you don't have any other thing to stop the whole process and maybe run another process in the CPU. But here, with multiple threads, each thread is another schedulable entity. So when this thread blocks, you can start running another thread, okay? So that other thread may start running, even though one thread has stopped and waiting for I/O to be done, okay? So now, again, some task is done as part of this process. Okay, so this piece of code is executed in that process, okay? So the system may decide that, okay, that thread has run long enough. Maybe it has run 100 milliseconds, so it may suspend that as well, like suspending the process, and another thread of that process can run. Assume when the program is started, you have created initially 3 threads. One is the main thread that is created by default, and you also created 2 other threads so that you have 3 threads here. Okay, you have 3 threads. So when one thread runs and blocks, you have another thread that you can schedule and run it for a while. and then it may run long enough, so the thread scheduler can decide to stop it for a while and run another thread, okay? So this is possible. But they are all running the same program, okay? But maybe different function of the same program, okay? Each thread may start running different function or the same function of the same program, okay? You will understand those better when we do some examples. But we are trying to introduce you now the threading concept, okay? So then, for example, that thread, when it blocks, so the IO with this thread was waiting may be completed. So this thread now can become eligible to run. So it can run, okay? And it can block later on. Then another thread run and so on, okay? So now, as a result, what we can have 3 threads running concurrently in a pseudo-parallel fashion, right? Of course, we have a single CPU. So now we are sharing the time that this process using in the CPU among the several threads of the same process, okay? Remember, in the multiprocessing idea, we were sharing the same single CPU among many processes. Here, we are sharing the same process among several threads, okay? Whenever this process has the opportunity to run in the CPU, now you can select one of these threads and run it for a while, and then another one, as long as that process is running in the CPU. Of course, when that process is taken out of CPU and another process is given the CPU, then you can no longer run the threads of that process, okay? So now you are scheduling the threads into the allocation or resources of that process. Yes?
Do you have only one PID for this process?
Yes, you have one PID, but you can have several thread IDs, okay? It depends on the implementation. Some operating systems consider everything as processes with some different type of sharing among them. But you can consider that you have as one single process ID, but you have several thread IDs. Now, the threads are a little bit, in some aspects, they are similar to processes, but they are also different, okay? Any questions? So as a result, what we have in a single thread process, we have a single thread of control, execution sequence, that is sometimes blocked and sometimes it is continuing and so on. In a multi-thread process, we have several execution flows, several threads, several activities. They are going in parallel, okay? Several activities, they are going in pseudo-parallel fashion. Not completely parallel, of course, because we have a single CPU. In a pseudo-parallel fashion, you are executing those several activities as part of the same process, okay? If, for example, this process has actually blocked here, a single thread process blocked for 10 minutes, no other activity can be done during this time. But if this would consider this multi-thread process, and if one of its threads has blocked for 10 minutes, you have another thread that could possibly run, another thread, and so on. So if you look to a time interval that's 10 minutes, in this one you will see that nothing has been executed. But here in this C, you will see that several activities are executed as part of that process, okay? So therefore, we have a pseudo-parallelism here among the threads that make up a process, all right? So this is the general idea. And here, what becomes from the scheduling perspective, we have now a process that is schedulable, right? From time to time, you schedule this process and run it in the CPU. And another time, you schedule that process and run it in the CPU. But now we have, as part of that process, 3 schedulable entities. You can select this thread and run it in the CPU, and then you can select this one, run it in the CPU, then select this one and run it in the CPU again. So you can now schedule the threads. So schedulable entities are increased. So threads become schedulable entities. So we can select one of them and run, okay? Of course, it depends on the scheduler, which thread to run first, okay? We should not make any assumption on that. If you create a thread, a new thread in your program, you cannot assume that that thread will immediately run or the existing thread will immediately run. You cannot make any assumption. But sooner or later, both of them will run, okay? This is the assumption that you can make. So let's do a more concrete example here. Assume we have a simple pseudocode here that is used to create some threads, okay? So we have a main function and we have several other functions. They assume this is your program, okay? So we have some statements here which are not shown. Assume this main function is doing that. It is doing something first and then creating another thread, okay? So when you create a thread, you can indicate to that thread as a parameter. So this is a thread creation function, okay? Into that function as a parameter, you can specify which function the thread will execute. So basically, this is a thread entry, thread start function. So that means when this thread is created, it starts executing from that point, from this function. This function will be executed in that thread, okay? Of course, this function can call anything here, depending on what you put. You are the programmer of this program. You can, for example, in this function, call this function or something else, okay? So it is, whatever you call here, that will be also executed as part of the thread. But this function, that means that this thread, whenever created, starts from here, okay? And let's say you start a thread at this point, and which is starting execution at this function, and then you do something else in your program. So at this, we have one thread here. At this point, we have created another thread, two threads. Then you try to create another thread. When this thread is created, where does it start to execute? You create another activity now, where that activity starts. Function 2, right? So that thread starts executing that, okay? But if you have some global variables here, all these global variables can be accessible from all of them. This function can access that, that function can access that, and so on. That means all these threads, activities, can access the same global variables. But each will have a different stack, because one thread may call this function, and that function may call something else. Just before finishing that function, another thread may be called, pushing some parameters into the stack. So each thread should use its own stack to push its functions, all right? The parameters of its function, because each thread will call a different sequence of functions and so on. And when one thread has pushed some parameters to its stack to call a function, another thread can run and push some parameters to call another function, and then complete that function and return those parameters. So that stack should be totally different than the stack of the previous thread, okay? So each thread has its own stack. Of course, each thread has its own CPU state as well, because they are different execution sequences. Each thread may be in different point in the program to execute next, okay? Each will have its own PC value pointing to the next instruction to execute, right? Initially, this thread will point to here, this first thread. The second thread will point here if they are started immediately, okay? And so on. So then this program is doing what? After creating that thread, again, it does something else, and then later it tries to create another thread, okay? It calls again a thread creation function, where you specify here the name of the function, which will be run as the first function in that, when that thread is created. So this is again thread function 1. So this thread was started and it was running here. Another thread is started and it will also start running from here. Okay, it's possible. Threads may run the same code. Okay, then it's up to the programmer what to call here and so on. It is totally up to you to design this. Okay, so then what will happen? So initially, when you write such a program, and then assume you compile that, and now you start running this program. Okay, you start running this program. So what will happen? In which point here will the program start running? Where does it start? Here, right? So it will start from there, okay? So assume it's executing, and at this point, assume it is creating a thread, okay? So what will happen then? It calls a thread creation function. A new thread will be created, right? Another execution flow thread will be created. So we have another thread now. Where does that thread start executing? Right? So it starts executing those functions, okay? Of course, while it is now, after that creating that thread, now this thread is ready to execute again, right? So now, at this point, for example, you have this thread, this main thread, and plus that thread 1 and thread 2, that can execute concurrently, right? So now, at that point, we have both of these processes, or threads, executing in the CPU in a pseudo-concurrent manner, pseudo-parallel manner, right? Of course, time-sharing manner, okay? But we are just showing that they are running in parallel, all right? So now what will happen? assume at that point, this thread will create another function, another thread. This main thread will create now another thread because it's calling thread create again. During this time, the second thread, of course, may continue doing something else. But of course, for thread creation, the CPU should be belonging to this process. Actually, that has to be stopped as well during this time. Anyway, so here again, at this point, that main thread will create another thread, right? So we will have the third thread created. So now that will start at which instruction or at which point in the program? Function 2, right? So it starts executing at that point. While it's executing, other threads can execute as well in a pseudo-parallel manner, right? Sharing the same CPU. One will run for a while in the CPU, another one will run for a while in the CPU, and so on. So we can have such a picture, all right? And then what will happen? Again, this program, when it comes to this point, all right, it will create another thread. So now that thread is created, and it will start executing at which function? Function 1, right? So that will run. So at this point in time, for example, we have 4 threads that are running in a pseudo-parallel manner in the system, okay? So this is the basic idea. They are running the same program, they are operating on the same program, they are using the same global data, okay? But they each has its own stack, each has its own CPU context, because each one is running as like a different process, okay? Each one is a different activity, okay? Represent a different activity. Any questions? Yes?
How about variables? The effect changes.
Yes,
Affects each other.
exactly. So they share the global variables. If you have a global variable here, integer global variable, whenever one thread changes that, and if another thread reads that global variable, it will see the change. Yes. Whenever you make a change in the global variable, everybody will see the change. Okay. So the global variables are totally shared. So if you increment a value here, then another thread that assigns the incremented value, that integer, to somebody else, then the incremented value will be assigned and so on. Okay. Yes. Yes, yeah, nasıl yani? Wow.
Yani aslında sormasına önemli şey, bir global variable da olsa fonksiyon 1 ve fonksiyon 2 için, fonksiyon 1 mesela bu global variable'ı değiştiriyor olsun.
Tabii.
Fonksiyon 2'nin de hani fonksiyon 2, fonksiyon 1'den daha sonra invoke edildiği için farklı, yani yeni haliyle görmesi lazım fonksiyon 2. Ama burada biz hani pseudo paralel iki prosesi, yani iki thread'i kullandığımız için o zaman yani fonksiyon 1'deki yapılan değişiklik fonksiyon 2 görmezse yani bilmiyorum hatta.
Right. Here you have, of course, some synchronization problems if you are doing in pseudo-parallel manner, okay? That will be discussed later on. There may be some problems. So you are not guaranteed that always this will be executed or that will be executed, okay, as part of different threads. But what you can do in a single-thread program is this. In a single-threaded program, you cannot create 2 activities that are running in a in a concurrent manner. If you call this function and then that function in a single-threaded program, the first function has to definitely complete before the second function is run, okay? Here, if you create a thread that is running this function and another thread that is running this function, then you don't know which function will be executed earlier. And you cannot make any assumption, this will execute or that will execute. So if there is a data dependency, which requires that logical data dependency, that requires that the data that's produced here will be used here, then you have to synchronize the threads. Ensure that the second thread is not running this function unless the first thread has finished running this function, and there are some mechanisms to do that, okay? But we will see that later. So you have to solve these problems with multi-threading idea. All right, then we have single and multi-threaded processes. A single-threaded process has a single thread, full of execution sequence of instructions that are executed, okay? So it has a set of registers, the program counter pointing to the instruction to be executed next, and so on. It has its own stack. It has a stack. It has code, set of instructions, text segment, code segment, global variables, data segment, and so on, open files, and so on. So this is the process address space, and the execution flow of the sequence of instruction execution as part of the process is represented by a thread, okay? But in a multi-threaded process, what we have the same code, one code, same set of instructions, one program, same set of global variables, same set of open files, and so on. They are all shared among the different activities that are created, among the different threads that are created. But each thread, here we have, for example, 3 activities, separate activities that are going on parallel, pseudo-parallel manner. 3 different threads. Each has its own set of registers, CPU state and so on. Because when this thread has stopped and another thread is to be run, the CPU registers has to be saved in the thread control block, and the CPU state has to be loaded from that thread control block, and this thread it becomes ready to run in the CPU. Okay. So therefore, each has its own set of registers. Each thread is represented again by a thread control block, like a process control block. Okay. And each thread also has its own stack. While this thread is executing, when it makes function calls, the parameters, local variables of the functions are pushed into the stack. Then that thread is suspended for a while. Another thread is run. It may make some function calls and so on. So these functions are, the parameters of them are pushed into that stack. Okay. Then it may be suspended, or it may continue executing and then exiting, returning from those functions. Then they will be popped up. Okay. If they push also the parameters of the functions that are called by that thread into here, then a mess will occur. Okay. So therefore, each thread has its own stack. All right. So then we will have such an environment where you can write programs. So the benefits of the threads are these: responsiveness, resource sharing, economy, and scalability. Basically, responsiveness means that if one thread blocks, you have another thread to run. All right? If one thread is doing heavy computation, another thread is waiting for user I/O. So you don't have to wait until that computation is finished for your keystrokes to be taken into the system. Okay? Because another thread, whenever you type, can take them into the system. Okay? Therefore, such a system or program may become more responsive. Resource sharing. Threads can easily share resources. Now we have a very strong primitive or facility to share data between the threads, the global variables. Remember how hard it was to share data between the processes. You have to create message queues or mailbox, or you have to create a shared memory. Now you don't have to do that. You just have a global variable, define a global variable. One thread can write data there, and another thread can read the data there. Okay, but of course you have to be careful about race conditions and synchronization problems that we will learn how to solve in chapter 6. Okay, and another benefit is economy. Creating a thread is very fast compared to creating a process, because you don't have to duplicate the code and global variables. And scalability. If you have a process that is running in a system with 4 processors, a single threaded process can only utilize 1 processor. But a process that has created 4 threads can utilize all the processes, because each thread can be run in a different processor. Okay, so threads, a multi-threading program can make better use of the multiprocessor architectures and machines. Okay, so we will continue with the other issues about threading.